board. Is there anything else I'm forgetting? Who knows? Okay, so that was nice of Nick to stop by. So they keep changing the name. I think it's the Learning Success Center now, or the Learning Center, or the Success Center. I don't know, they always change the name. But what I'll do is I'll post the link, but you can find it pretty easily, but I'll post the link to the Learning Center just so we have it on our Moodle page. So Nick, I think it was K. Ben, can offer additional help in, I'm going to call it the Learning Success Center. In the Learning Success Center. Okay, so he did that little intro. He showed you how to get there, but I'll post the link just in case. So what's really nice is that the Learning Success Center, I usually mention it on the first day. Can't remember if I did or not. Usually I do. And it's free tutoring. Right, and so here you have free tutoring. So Nick, for example, is kind of the math stats guy right now. Kate can also help you for a lot of this stuff. And we were talking about, Kate knows everything. It's insane how much she knows. Chemistry, physics, math, calculus, whatever. She knows it all. And so they're already paid by the college. And so try to make use of what they have to offer, right? So it is free tutoring for you. Their time is paid for already, so you may as well use them. Now, this course, in terms of the material, and we were kind of chatting about this before class started, if you came in before class, we were talking about, okay, so this course itself is being restructured, and it is to benefit the data science program. They want more solid math skills, kind of theoretical skills, and so that's what we're going to be working on mostly. So the name applied statistics is going to be misleading this term, just because there was no time to change the course. So we're just going to solidify kind of our mathematical statistics, which is all theoretical or mostly theoretical. It also means that the lab portion, because right, we have class and then we have a lab section. I'm having a hard time figuring out what we should be doing in the lab section. So I might just use it to solidify your R skills, right? And so depending on how comfortable you are with R, that might be totally boring, or it might be useful, right? And so, but it never hurts to solidify skills, right? Okay, so that's kind of a heads up. I know that's not really useful, but it just like I ask them to come in from the Success Center. I wait a few weeks until some of the material has we've introduced some of the material, and now free tutoring might sound, hey, that's a good idea, right? And so that's why I wait a little bit, so you can see the benefit. But we haven't had too much due, and that's because we're still kind of introducing concepts, right? And so I like to let it build up, and then we'll start working through stuff. But I did post, let's see if I can get there. Not that. It's gonna ask me to log in, I think. I did post from the lab last Friday. I posted a Hello World assignment. It's really just going to be kind of showing off the skills and the things that we talked about in the lab on Friday. So I'm calling it lab 1 or a Hello World assignment. So I posted the assignment here, and notice that it's just going to be the RMD file because Moodle can't handle RMD. It doesn't like the RMD extension, so it just makes it a text file. But what you would need to do is you would copy all of this, open up a new RMD file, and then you're going to erase everything in it and just paste this in there. And then you can save it and you have this new RMD file. And so some of these things we talked about, or a lot of these things we talked about. Saved photos, good. Let me bring it in. Okay. And some of these things we didn't talk about, but I feel confident enough in your skills to kind of nudge you out of the nest, so to speak. Right. And so first thing I want you to do is just create this assignment, and you can have the questions in there or not, it doesn't matter. But first I want you to write your name in bold, then italicized, then bold and italicized, right? We practice that in the lab. Then practicing some headers, bullet lists, numbered lists. How do the numbered lists work? This one, we did not talk about in the lab, but this is one of those things where you have to go out and you have to Google, how do I make this thing, right? And so I want you to insert a table in Markdown with 3 columns, right? So boom, 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 4 rows, 1, 2, 3, 4, as well as a header row. So technically 5 rows, okay? So you can make up information to add to the table if you'd like, right? Or you can leave it empty, but I just want to see that you can make that table. I feel like this should say up. You can make up information to add to the table if you would like, right? Or just leave it empty or whatever. So then I want you to make a new R code chunk, and then in that R code chunk, I want you to calculate this number. And so you're only going to be able to see what it is once you knit this document here, right? So you'll want to bring it in so you can see what's going on. But what it should end up looking like is, this is a fraction where 4 minus 3 is at the top, and 1.2 divided by the square root of 45 is in the denominator. Okay, here I've used these dollar signs, and you might have used them before to insert a LaTeX chunk, right? And so LaTeX is a typesetting language. So this here is LaTeX. And you spell it with a capital L, lowercase a, capital T, lowercase e, capital X, LaTeX, okay? And it's just a typesetting language. It has all these different built-in, I guess, functions. So if instead of typing out mu, for example, we can do something like $/mu, $, would generate mu. Okay, so in terms of a cow, how do I draw a cow? That doesn't look like a cow. So anyways, that didn't look like a cow at all. So for example, if there are symbols that you need, then the language that you should look them up in is LaTeX, right? How do I type a fraction in LaTeX? Well, you can use the /frac. Okay. So I've included this code so that you can see it, so that you can dissect it and kind of learn from it, right? And then if you want to look up kind of other ways to write fancy things, especially mathematical formulas, then the language we'll use is Latex. So I want you to calculate it, and then I think it says, oh yeah, describe briefly how the answer is displayed. It's very, very brief and very, very obvious. So I'm not looking for a huge explanation. It is just going to show the answer below, right? And so that's basically the answer. Then I want you to end it by saying, add a comment to your R code chunk, saying the end. Okay. Then knit your document, and then I want you to submit it on Moodle. And I think I made it due, let me check here though. I think I made it due on Tuesday, next Tuesday. Yeah, due Tuesday, September 28th at 11:59 p.m. So I like to do midnight for most submissions. Okay, and so this is due Tuesday, September 28th. I guess I can add the year, should be this year, at 11:59 p.m. Okay. So you can work through that. Like I said, most of it is really easy, and some of it you might have to look up. Okay. All right.
Sorry, excuse me. This table is in Markdown. Should you use like LaTeX or can we like do a what's the name of it? A data frame in R and then just print it? Is it supposed to be using just Markdown, just LaTeX?
I was thinking just Markdown, but
right.
The key is that you're able to generate a table. So however you want to do that. So I said in Markdown, right? Or however you want to generate some sort of table that you can enter stuff into. I'm fine with that, right? Or LaTeX. Or even R, if you want to. Because
Okay,
R can generate a table.
Thanks.
Awesome. But what I had in mind was just a quick Markdown table. But if you want to get fancy, you can. Okay. Good. All right. So, oh yeah, last week I had the dog and we had to cut it short, and then I posted the recording. So hopefully you're all caught up on the recording. If you're following along in that chapter that I posted on Moodle, I skipped some things towards the end there. Specifically, I skipped some of the integrals and some of the summations. I want to hold off on introducing those for a little bit longer, and just introduce some of these key concepts first, and then we'll introduce the integration and the sums as we need them. Okay, so they are coming, but kind of a more toned down version. So that's kind of it for, sorry, I've got a little thing there. Okay, so in terms of review, I want to just kind of leave that from last week, especially if you haven't had a chance to watch that video yet. Then we'll touch on it a little bit, but what we're going to do is we're going to start a new section today. So that section is section 1.3, and it is on the probability set function. probability set function. So far, we haven't really talked about probabilities. We've talked about sets, right? We've talked about elements of the sets, notation, so set notation, elements, subsets, that kind of thing, right? And so now we're going to introduce the probability of a set, okay? So a set of outcomes. But of course, we need to lay some groundwork here. And so we're going to let that fancy C be the sample space still. Okay, so that's going to stay the same throughout the course, but we're going to introduce it here. So let's see. Oh, that was a bad C. Remember, I'm trying to do it with a little tail on here for kind of a script C. Let's C be the sample space of all possible outcomes. We're used to that by now, right? So what we want to do is we want to assign probabilities to subsets or events, right? And so those are subsets of the sample space. We want to assign probabilities to events. Now, events are just subsets of C, which is the sample space. So, all right, good. We're going to introduce another letter, which is kind of a script B. So I'm going to have it put a little curl on it again. And B is going to be the collection of all possible events, right? And so events are subsets of C, right? So events are subsets of the sample space. And so now we're going to have B, a script B, denote all possible events. Okay. Here, I'll clarify, right, that events are subsets of C, right? That's what we say there. And then we use that. So we will let this kind of script B denote the collection of all possible events. Right, and so events, I'll highlight that. Events are subsets of the sample space, whereas the sample space is the collection of all possible outcomes. So that's the difference between the two. Just as a side note, we will assume the sample space C is finite. Okay, that is an assumption that we're making, and that's not necessarily true, but for most things, it will be true where the sample space is finite, right? If you have an infinite sample space, then that changes things, but we're not going to consider that potentially at all in this course. I'm not 100% sure yet. So we're going to consider a finite sample space. Okay. So the technical definition of probability is made up of 3 parts. Okay, and so what I want to do is show you that you already know these facts from Stat 230. right? But I want to show them to you in more of a mathematical notation way, right? So in more of an official way. So everything that we're going to develop today, you will have seen in Stat 230. But in Stat 230, we just say, here it is, and we don't really explain why. So now we're going to look at some of the reasons why those facts work. Okay, so that's what we're building up towards. But if at the end of the day, you feel like, I don't know, she didn't really cover anything new, I knew all that already, that's good, right? But what we're trying to do is we're trying to develop why those things work, right? And some of the reasons why we're able to use them. Okay, so probability in terms of what is it, we're going to develop the definition, I guess, by saying that if we let C be a sample space, and let script B be the set of events, right? Just as we established earlier, we're going to let P be some function that's defined on B, all the subsets. So we're going to let P be a real valued, and that's just to indicate that we're not going to work with imaginary numbers. We're going to leave those alone, and we're just going to work with real numbers. So real valued function defined on B, or script B, I should say. Okay. So just laying out the lay of the land, here's all the things that we're going to be working with, and here's what they mean in this case, but that's generally the case. Then P is a probability set function if P satisfies the following. Okay. And again, these are going to be familiar. First, if the probability of A is greater than or equal to 0 for all A in B. Are you guys okay with this? This means for all. A little shorthand for you. We get lazy, right? Usually it just ends up being just a bunch of symbols together. Hey, isn't that any language? Yes, but it's shorthand for the English language. So for all A that are elements of B, okay. Yeah, a little shorthand. Yeah, I shouldn't put a circle around it, right? Yeah, no. But I mean, maybe there's deeper meaning there for all. Anyways, I digress. So here, what all we're saying is that the first step in being a valid probability set function, which is really just a probability function. Usually we drop the word set eventually, and I'll make a note of that later. But the first step is that the probability has to be greater than 0. We also know probably from Stat 230 that it has to be between 0 and 1, but we're going to develop that fact. Okay, so for now, just to be a probability, the probability has to be larger than 0. Okay, for all sets of A that are contained in B, which is the set of all possible subsets. Whoa. Okay. Okay. The second thing that has to be satisfied is that the probability of the sample space has to be 1. And again, that is also familiar from before, right? So the probability of the entire sample space of anything that could happen is going to happen should be 1, right? If there's no other restriction on what can happen there, that's a nicer C. So the third element is the one that I typically just kind of gloss over in Stat 230, but we're going to bring it to the forefront here because it's part of developing this theory. So we're going to rely on the following a lot. First, what I want to do is I want to write it out just classic with a bunch of notation, and it's going to look kind of nasty. And then I'll write a simplified version. Okay. Or I'll try to write a simplified version. How about that? So if the set of AN is a sequence of events in the set B, and A subscript M and or intersection A subscript N is the empty set, okay, for all M not equal to N. What does this mean? It means that for any A and another A, so for a set, for the first set and the second set, to have the empty set in common, right, means that they're disjoint, right? So here, let's call this set 1, and this is set 2, right? What this is saying, and let's see if I can get more colors here. Set 1 and set 2 are disjoint for all M not equal to N, assuming that they're not the same set, right? If set 1 and then is the same as set 2, then of course they're not disjoint anymore, right? Assuming that they're two different sets. Oops. Assuming the sets are not the same. Right, that's what it's saying. Okay, so overall, what we're saying here is that, let's see here. I don't want to circle this whole blurb, right? But really what we can say is that we say A AM and AN are pairwise disjoint. And we just use the AM and the AN to denote that these are two different sets, right? And so you could have A1 and A2 versus A1 and A3, A4 and A5, right? So any combination of two pairs, they're going to be disjoint, right? So that's what it's saying. So if we have a sequence of events, A1 and A2, for example, right, assuming that they're disjoint, right, pairwise disjoint, then, hey, that wasn't even it. Then the probability of the union from n equals 1 to infinity of AN, right, the simplified version is if we only consider A1 and A2, right, then the probability of A1 or A2, okay, is going to be the sum from n equals 1 to infinity of the probabilities of AN. Right. Right, consider n equals 2, right? Then what we're saying is that the probability of A1 or A2 is the probability of A1 plus the probability of A2. Okay. It hinges on them being pairwise disjoint, right? So assuming that A1 and A2 are disjoint. Assuming A1 and A2 are disjoint. Right, so this might also look familiar from before, right? But we never ever would have written it like this in Stat 230, never, right? Or I wouldn't. It's just mean, right? We can extend it to more than one union, right? So here, this is one union, A1 or A2, or A1 union A2 if you prefer, but I like to read it as or because it helps me kind of grasp what's going on, right? So here what it's saying is that you could have a union from A1 or A2 or A3 or A4 all the way up to A infinity, technically, okay? So the probability of those unions together is the sum of the probabilities, right? So here, the sum is here, right? The probability of A1 plus the probability of A2. That's the sum of the probability of A1 and A2. Question?
Yeah, like can you show an example? I'm not able to gauge the first part, the left part of the equation. Like maybe an example with like a small set of like 5 numbers or something.
For this one here?
Yeah.
Yeah. Do you want me to show it to you? Sorry, my speakers are not that great. You want me to show with more than 2? Yeah. So what we're going to say is that if we're talking about, yeah, let's do 4 elements. Good. So if we want the probability, so just as a quick example here, if we want the probability of the union from n equals 1 to 4 of AN, just to keep it with the same notation, then that's going to translate to the sum of n equals 1 to 4 the probability of AN. Now what this is going to look like, the condensed union here that we have is going to turn into, when I write it out, it's going to be A1 or A2 or A3, oops, or A4, which is going to be the probability of A1 plus the probability of A2 plus the probability of A3 plus the probability of A4. So that's what it's saying, assuming that A1, oh, I sure am, thank you. There, nothing happened. It's important. Yeah, good. So now, right, it hinges on A1 having no elements in common with A2, A1 having no elements in common with A3, and A1 having no elements in common with A4. And then we'd have to cycle through and look at all the possible pairs, right? And so here, again, I'm going to write that assuming there are, or maybe I should say it in like this instead, assuming these are all pairwise disjoint. Meaning what? Meaning the probability of, and maybe not even the probability, I think we can just say the sets, yeah, because it's elements in common, meaning A1 and A2 is the empty set. Oops. A1 and A3 is the empty set. Oops. Ha. Forget an A. Can we have duplicate values in a set? Yes. But we wouldn't list more. So each value would only be listed once. But you could. So the only thing I can think of is that A1 and A1 does not equal the empty set, right? So then it doesn't work. Oh, no, we need them all to be pairwise disjoint because if there's overlap at any point, then it's not going to work. We're going to get there. And you probably remember the formula, right? Because we have to subtract the overlap. But so it only works if they are all unique. Good. And so, and kind of so on and so forth, going through kind of A2 and A4, for example, equals the empty set, etc. Okay. Good. Okay. So let's see here. Where were we? Oh yeah, we dissected this kind of crazy notation, but it's just a list of the unions. And then what we can do if they're pairwise disjoint. So assuming that all the possible pairs are all disjoint, then you can add up those probabilities. Okay. And so just as a side note, if we find that the sum from n equals 1 to infinity of the probability of an equals 1, what does that mean? it means that we've added up all the probabilities and we found a total of 1. The total of 1 means that we have the sample space, right? So a universal set, nice. And we call this collection of events exhaustive, right? Because we've exhausted the sample space. And so the collection of events is exhaustive, right? Since, and I'll put here, since the entire sample space is included, right? So we've touched on probabilities, and I've had a hard time not mentioning probabilities yet, but here we're going to start introducing the probability aspect, but it is exactly what you think it is. For most scenarios where we have we call them equilikely cases, equilikely meaning they're equally likely, then we just take the number of possible outcomes as our denominator and the number of outcomes that we're interested in the numerator, right? And so that's where we're building towards. So a probability set function later we'll just call it a probability function, later called probability function. But for now, we just want to emphasize that we're applying the function on a set, right? So a probability set function tells us how the probability is distributed, how the probability is distributed over the set of events and this script B that I screwed up there. Hang on. There. So the probability set function has some key properties that we're going to use, and some of them build on the previous one. And so what you're going to find is that we're going to develop kind of this toolkit of useful theorems that we're going to apply, right? And so some of them are more obvious than others, okay? But as soon as we've stated it as a theorem, we're allowed to use it and apply it in proofs, right? And so some properties of probability set functions. Yeah. I am going to use the same numbering as the textbook, just because then if we need to refer to each theorem, then we can do that, right? And so I just want to keep the same labeling as the textbook so that there's no confusion. So we'll start with theorem 1.3.1, which is the theorem that says that for each event A that's an element of B, right? And this is kind of that fancy B. The probability of A is 1 minus the probability of the complement of A. that's an obvious statement, right? Because if I told you that the probability that you will not pass this course, right? If A is passing the course, then the probability that you do not pass this course is 5%. What's the probability that you pass the course then? 95%, right? 1 minus 0.05 is 0.95. So the probability is 0.95 then, right? And so this theorem is obvious. It's an obvious statement. But we don't see it like this very often. So, all right. So what we want to do is we want to work through the proof, right? So the proof for why this is true. I'll use a different color here, and maybe I'll do kind of dark green. How do we prove this? Well, that's a pickle, right? Especially with our first proof in this course. I don't think I've done a proof yet. I tend to avoid them. No, I like proofs. Proofs are one of those things that if you work on them, then you get better at them, right? That's true for everything, but especially proofs, right? The more you have, exactly, it helps your intuition, right? Oh, I've seen something similar to this before, right? And so the more you see, the more you'll have to kind of, oh, let me try this. I tried this before, it worked, right? And so on. So for the proof, what we're going to say is that, okay, well, we can talk about A and the complement of A. We've already defined the complement of A as everything that's not in A, right? But also in the sample space. So we can bring the sample space into this, and that's kind of a common thing. So what we have the sample space is everything in A or not in A. I think we can all agree that that is the sample space, right? If we have a look at kind of the Venn diagram here, if I have A, and remember everything in the rectangle is the sample space, right? And so if I'm looking at everything in A, right? So that's here. Or not in A. Well, not in A is everything on the outside here. So wait. So it looks like that's the entire sample space that's been shaded, right? So I'll use this quite a bit just to convince myself that what I'm saying makes sense, right? And so I encourage you to do the same. And in this case, right, we're saying that, okay, I'm going to break up the sample space as A or not A, or the complement of A. And we're also going to declare that A and not A is the empty set. Okay. Why am I setting it up this way? Right? That's not obvious, especially with our first one. Why am I doing that? Well, it's because I have very, very few tools here to help me, right? But the one thing that I do know is what we just established here, right? I know that if I have a sequence of events, for example, A and the complement of A, as long as A and the complement of A is the empty set for any set A, then we can apply this, right? I can find the probability of the union of A and not A is going to be the probability of A plus the probability of not A, right? And so that's kind of where I'm going. So I'm trying to match things that I know already, things that have been established that I can use. Okay. Let me catch up here. Okay. So, and since the probability of the sample space is 1, that's a fact. Okay. That was one of the conditions for a valid probability. So we are assuming that we have a valid probability function. And so then the probability of the sample space has to be 1. We know that the probability of the union from n equals 1 to infinity of an is the sum from n equals 1 to infinity. Oops, that should be infinity of the probability of an. Okay. So what we can do is, okay, I know I can define C in terms of A and the complement of A, which matches back to what I started with, right? But I also know the probability of C, right? And then I'm able to establish that A and the complement of A have nothing in common. And so we see that the probability of C can be written as the probability of, now I'm going to replace C with A or A naught, or the complement of A. Okay. So that's going to map back to this, right? The probability of A union the not A is going to be the probability of A plus the probability of not A. On that side. Okay. So in this case, I did do double equal signs. Typically, I like to stack my equal signs, but I had a page break here, but that's not the reason I did it. The reason I did it is because these all equal the same thing. And so what I actually want to establish is I want to establish the link between the sample space and these individual probabilities, right? And so this was just kind of a go-between. Okay, but so now what I can do is I also know we know the probability of the sample space is 1 by definition, but then I can replace the probability of the sample space with these two individual probabilities, the probability of A plus the probability of the complement of A is 1. Okay. And we know that those two events are disjoint. So now I can rearrange this and solve for the probability of A by subtracting the probability of the complement of A from the right-hand side. And so I have the probability of A is 1 minus the probability of the complement of A. And that is the end of that proof. So usually we'll do like a little box that's shaded in. Okay. Are you saying that Venn diagrams make it easy or that they're not making it easy? Replying to a direct message here. Yeah, so we use Venn diagrams. I use them to convince myself that what I'm saying makes sense, right? So does it make sense for me to declare that the sample space can be denoted as A union the complement of A, right? And so here I just convince myself that yes, it does, right? And then everything just kind of falls from there. So in terms of proving things this way, it's really just a matter of working up our mathematical stamina, right? And so proofs are hard, right? Yeah. Exactly. Right. And so we're just kind of exercising things that we've learned and applying them as we go. Okay. Is this a real life application? No, absolutely not. But being able to take things that you know and applying them to a new problem, that's definitely something that you need to be able to do, right? And so this is just one of the ways that we can practice that. Okay? Even though it doesn't feel like it, I promise. That's how it's going to work out. In case you're not familiar with, you trust me. Oh no. In case you're not familiar with this little box at the end, this is really just the end of the proof. You might have heard QED, right? And so just kind of as a note, a box filled in or empty, I don't think it matters. I've used both. A box filled in or empty means QED. Some people just write QED and it signifies the end of a proof. But QED, I have it here just because, yeah, so you box the answer. In this case, the answer is everything that you've written, right? And so here, yeah, so in the chat, I got a direct message that says in India, you box the answers, and that's pretty typical, right? But here, everything that you wrote is the answer. So now you just put the box at the bottom. So QED stands for Quod Erat Demonstratum. Demonstrandum, sorry. Which is, of course, Latin. Latin for that which was to be demonstrated, was to be demonstrated. Okay. Either one of those, they signify the end of a proof. Okay, so you can write QED, you can do a box, you can do a filled in box, but either way, you should signal that, hey, that's the end of my proof, right? Everything I needed to say, everything that was to be demonstrated has been demonstrated, right? That's just a little fun fact, but that's where it comes from. Okay. The next theorem I want to talk about is 1.3.2, specifically that the probability is, yeah, it should only be used in the end of a proof. Yeah, exactly, good. So not just a calculation, but a proof. I guess technically a calculation is a proof, but you should only use them for mathematical proofs. I wouldn't be upset if you did a calculation and put a little box, that's fine. So 1.3.2, oh yeah, the probability of the null set should be what? 0. The probability of the null set, which is nothing happening. If you do an experiment that's going to yield one outcome, right, at least one thing, then the probability of nothing happening when you did that experiment should be 0, right? And so the probability of the null set is 0. Notation wise, what we're proving is that the probability of the empty set is 0. The empty set is the null set. It's the set of nothing. Okay. So remember I said I inserted that, okay, the complement of the empty set is the sample space, right? The opposite of nothing happening is everything happening, right? And so now we're going to leverage that and say that, okay, here we go. Try to use green again. In terms of our proof, right, we're going to use the previous theorem. So in theorem 1.3.1, let A be the empty set. Okay, so what I'm going to do is I'm going to scroll up to theorem 1.3.1. A is the empty set here. So then what I'm going to do is I'm going to have the probability of the empty set is going to be 1 minus the probability of the complement of the empty set. But then remember that the complement of the empty set is the sample space, but also the probability of the sample space is 1, right? I find that a lot of the time, I just kind of end up searching for things that might work, and usually things start to fall out, right? So I'll show you what I mean by that. So, so that the complement of A is the empty set, the complement of the empty set, which we said, can't remember if it was last day or the day before even, that's going to be the sample space, right? So that's a fact. Okay. Then we find the probability of the empty set is 1 minus the probability of the complement of the empty set, which is 1 minus the probability of the sample space, right? Which is 1 minus 1. And all along here, I'll fill it in this time. Usually if nothing's changing on one side, I don't bother writing it out again. Right? I'll make a note of that because that might come up, right? Especially if you have a lot of text on one side and it's not changing, then you don't need to write it out. If one side of an equation, well, one side has to change, otherwise why would you write a new line? But if one side of an equation doesn't change, we do not need to write them out. need to write it out. Okay. So what does that mean? It means that the probability of the empty set is 1 minus 1, which we know is 0. But don't worry, I'll have you questioning even that. The more math you do, the more kind of, oh, is that true? Do I know the proof for that? Can I prove that? I think, is it the proof for 1 plus 1 equals 2? I'm pretty sure it's like 3 pages long, because it has to draw on all these different theorems to get there, right? And so even the most simple statements have potentially huge proofs. Yeah, it's worth looking into. It's kind of fun, but good. So this one, well, once we knew what to do, right? Yeah, exactly. Mathematical induction. Once we knew what to do, then the proof was easy. The proof itself is rarely hard. It's just figuring out which components you can use to get to the result that you want to prove. Yeah. Am I running out of time? Time flies when you're having fun. Let me just, I don't know why I'm having such a hard time. I think it's because we start at past. All my other classes, I just start. Oh my gosh. I am running out of time. Okay. And I've got a biggie coming up. Let's start it. I'll make the statement and then we'll see where we get to. So the next theorem, 1.3.3, says that if A and B are events such that A is a subset of B, right? So A is contained in B is how I read it, but it should be a subset of B if you want to be proper, but a subset is contained inside that other set, right? So that's why it works the way I say it. Then the probability of A is less than or equal to the probability of B. Okay, that seems fair enough. Okay, but what we want to do is we want to prove it, right? Why is this true? So if we think about it, first let's convince ourselves, because I am running out of time here, first let's convince ourselves that it makes sense, that this is a logical statement. So if A is a subset of B, okay, then what this is going to look like, if I have my sample space here, is I have B, which is potentially quite large, and then A is some subset contained in B. Okay. Then thinking about probabilities as the number of outcomes over the total possible outcomes, well then if A is inside B, then the total number of outcomes is less than or equal to the total number of outcomes in B, right? And same thing, the probability of B is all the outcomes in B divided by the sample space, right? The size of the sample space. So it seems logical enough, but what I'll do is I'll let you guys try it. It's in the textbook, which is posted, right? Chapter 1 I posted so that you would have something to start off with. But try it. Try to use the things that we've developed so far. For example, try to use the unions, right, of disjoint events, right? So rewrite A and B as unions of disjoint events, and see where things take you. Okay, so try it. Try on your own for next day. We're going to go through it, obviously, but it might be fun. I'm not going to check it or anything, but try proving it on your own. If you have any questions, let me know. Otherwise, I'll see you on Thursday. And I'll stop this recording here.